All right, we're going to go ahead and get started. Before I get into the technical stuff, we'll do a little bit of logistics. So we are starting these things called sessions. We announced them on Piazza. If you're not getting our Piazza stuff, definitely make sure to sign up for Piazza or send us a note. The sessions are designed to go into the material a little bit deeper, also to discuss something about the homework. They're a structured session as opposed to an office hour where you can ask one-on-one questions about the homework. The sessions are designed to go a little bit deeper into the material, and they were prompted both based on some colleagues of mine feedback of how much students have liked them in their other classes, as well as some requests from last year for opportunities to go deeper into the material. So we've announced these on Piazza. The idea is that you will sign up for a session. They are optional. You don't have to do them. We will be giving 1% extra credit for attending them if you attend a sufficient number of them. The details for that has also been announced. And I think that's true. If I've got that wrong, just email me. I think that's been announced also on Piazza. So if you go to Piazza, there's a number of different sessions you can sign up for. The point of signing up for them is to make sure that we have room capacity, but I'm pretty sure we'll be able to accommodate almost any session you want to go to. The last session will be done via Zoom and is particularly targeted at SCPD students, but anyone is welcome to do it. The way that we will be keeping track of whether or not people are going to sessions or not is we will have a code that's mentioned inside of the material. And so then you will just write in that code to indicate your attendance. We will record the last session so that if for some reason your schedule is such that you can't attend any of these, but you want to participate in session, you can go through the material later and then record that you attended it by using that code. And we'll be relying on the Stanford Honor Code that only people that are doing this will upload the codes. Does anybody have any question about sessions and what those involve? Again, they're optional. They're a way to go deeper into the material. Some other people have really liked these sort of things. You can see what you think. It's an experiment. All right, any questions about anything else outside of sessions? So homework's been released. Office hours are happening as usual this week. Feel free to come talk to us or use Piazza for any questions that you have. All right, we're going to go ahead and get started now then. As usual, I really appreciate it if you use your name whenever you're asking a question or making a comment. So today we're going to finally start to get into making decisions where we don't have a model of the world. And in particular, we're going to be focusing on model-free control. So the things that we're going to be covering today is really focusing on how can an agent start to be making good decisions when it doesn't know how the world works, and it's not going to be explicitly constructing a model. And remember, a model in this case is going to be a reward and or a dynamics model of the environment. So today we're going to be looking at methods that do not involve constructing a dynamics or a reward model, but it's just going to be directly learning from experience. So before, we were mostly talking last time about, well, maybe we don't know how the world works. We don't have these explicit dynamics and reward models, but we're going to be trying to evaluate a policy that was provided to us. And now we're going to be thinking about the real problem that often comes up in reinforcement learning, which is how should an agent make decisions when they don't know how the world works, and they still want to maximize their expected discounted sum of rewards. So when we think about sort of how good is a policy, as soon as we have information about how good a policy is, then we can start to think about how do we learn a good policy instead. And in fact, when we started off at the very start of the class, we talked about how you would learn to make good decisions, or how you would compute good decisions if you were given a model of the world. And so that's what we're going to be going back to now. So in particular, now we can think of starting to get at this issue of this optimization and exploration. We're still not going to get into generalization yet. This will be happening soon. We've already seen this a little bit. This even came up with planning. But now we're going to start to think about how do we explore and how do we do optimization. So when we think about, well, I think I'm just going to go through more of these as we start to go into this area. So again, we're going to be thinking about how do we identify a policy that has a high expected discounted sum of rewards. There's going to be delayed consequences, which means as our agent takes actions, it may not see the result of whether or not those actions were good or bad for a while. And we're going to start to think about this exploration aspect. Okay, so let's start with where these types of problems come up and where people model things when we're thinking about markup decision processes and maybe not building a model. So I think probably one of the first really big examples of success for doing reinforcement learning and doing it in this sort of model-free way was for backgammon, which was roughly 1994. And they trained an agent to play backgammon, the board game, actually using a neural network. Neural networks went sort of out of fashion for probably around 10, 15 years and then came back. But in the early 90s, people were using neural networks. Jerry Tesaro used it for backgammon and got some very nice results. And that was sort of one of the first demonstrations of reinforcement learning in kind of a larger setting, that you could solve these sort of complicated games. Many other problems can also be modeled as an MDP, whether games or robots or customer ad selection or invasive species management. And in many of these cases, we don't know the models in advance. So what we're going to be thinking about today is situations in particular, mostly here, where we think about the model being unknown, but we can sample it. But there are occasionally cases too where you do know the model, but it's really, really expensive. So for something like computational sustainability or climate modeling, you might be able to write down a good model of the world, but it's really, really expensive to run because actually simulating the climate is really, really hard. And even then, your model will probably be impossible. But I raise this second point in the sense that when we mostly think about sort of learning from the world, we think of a robot like running around in the world and that being an expensive thing to do because robots are taking real time to do this. But you can also think about agents that are learning to sort of interact with a simulator where that's also really costly. All right, so what we're going to be thinking about mostly today is what is known as on-policy learning, where we get direct experience about the world, and then we try to use it to estimate and evaluate a policy from that experience. But we're also going to start to talk more about off-policy learning, where we get data about the world and we use it to estimate alternative ways of doing things. So we can kind of combine experience from trying out different things to try to learn about something we didn't do by itself. And this third thing is really important. The second thing is really important, so I'm just going to talk about it briefly up here. So imagine you have a case where, say there's only a single state for now, but like you have a state S1, you do A1, you stay in S1, then you do A1, or you're in S1, you do A2, stay in S1, and then you do A2. So you'd like to be able to kind of combine between these experiences so you could learn about doing this, even though you've never done that in the world. You've never experienced that full trajectory, but you'd like to be able to sort of extrapolate from that prior experience. So this sort of policy would be an off-policy learning because it's different than the previous policies we've tried. We'll go into that more when we think about Q-learning. All right, so let's start with generalized policy iteration. Okay, so if we go back to policy iteration, we talked about that a couple lectures ago. In policy iteration, we originally saw it when we knew the model of the world. So it was a way for us to compute what was the right thing to do, given right thing meaning the policy that maximizes our expected discounted sum of rewards. So how do we do this when we know how the world works? We're given our dynamics and reward model. In that case, we initialize some policy, probably randomly. So initializing, again, would mean that we'd set pi of s equal to some a for all s. And this is generally probably going to be chosen at random. And then we did this policy evaluation procedure where we first computed the current value of the policy, and then we updated the policy. So we took whatever we had, and then we did this sort of one more thing, which you can think of as kind of doing one more Bellman backup, where we said, okay, we're taking that v pi, we're plugging it in over to here. We're using the fact that we know the dynamics model and we know the reward model, and we're computing this one-step updated pi prime. And we talked about the fact that when we do this, we actually get monotonic policy improvement. Which is sometimes referred to as the policy improvement theorem. So this procedure, when we were doing it with sort of in this case where we knew the dynamics model and we knew the reward model, was guaranteed to always give us a policy that was at least as good as the previous policy or better. And eventually it was guaranteed to converge, at least in the case where we have finite states and actions, because there was only a finite number of policies. So in this case, there were only a to the s possible policies. So we'd only do this whole procedure at most a to the s times. because each time we're either picking a better policy or we're staying the same. And once you find the same policy, you're done. So now we want to do all of this, but we don't have access to the dynamics or reward model. So does anybody have any ideas of how we might be able to do the same thing now that we don't know the dynamics or reward? Yeah.
You can maintain a matrix of transition probabilities that you calculate as you experience the work.
Yes, the suggestion is, well, what if we try to, if I interpret correctly, what if we try to basically estimate a dynamics model and a reward model from the world, and then we could use this to, you could still compute your value function, maybe using some of the methods we saw last time, and then you could do this update, this policy improvement, using your estimated dynamics and reward model of the world. That's a completely reasonable thing to do. I may have any other ideas of what we could do. Yeah, name and.
Actually?
I think instead of having to compute a model, can we do away with the model and directly try to estimate what is the value of a particular state or associated action, state action pairs? So we just, without doing away with the model, we just estimate the value of a particular state.
A particular state in action? Yes. And was it Ashby? Yeah, so what Ashby said is exactly the path we're going to look about today, which is we're going to focus on model-free control. So we're not going to directly estimate a model today. I'm actually personally very partial to models. They can be very sample efficient. But for today, we're not going to look at that. And we're going to do exactly what was just proposed, which is we're going to compute a Q. And if we compute a Q function, which just to remember, Q is always a function of state in action. We're going to estimate the Q function directly, and after we have that, then we can do policy improvement directly using that Q function. So how would we do that? So this is Monte Carlo for on-policy Q evaluation, and it's going to look very similar to Monte Carlo for on-policy value evaluation, but we have to make a couple modifications. So before, if we were doing this for V, I'm just going to write it to kind of contrast. So for V, we just had a count of the number of states. Now we have a count of the number of state action pairs. Before, we could just keep track of G here, which can be the sum of previous rewards we've seen across all episodes for G of S. Now we're going to do that for S comma A. And then now we're going to, instead of having a value function, we're going to have a Q pi. So essentially, almost everywhere where we just had S before, now we have S comma A. And then it's going to look very similar. So we're going to assume that we're still provided a policy. We can sample an episode. And then we compute GIT for every single time step. And that, remember, now is going to, I mean, it was before, but we're going to think about the fact that it was also associated with a particular state and a particular action for that time step. And then for every state action pair, instead of just state visited in the episode, either for every first time we saw that state action pair or every time we saw that state action pair, we can always, just like before, we can either have first visit or every visit. Then we're just going to update our counts, update our sum of total rewards, and then estimate our Q function. So it's basically exactly the same as before, except for now we're doing everything over state action pairs. Now, once we have that, now policy improvement is even simpler than before. So we're given this estimate of the Q function. And now we can just directly take an argmax over it. So we define our new policy to simply be argmax of the previous one. All right. So does anybody see any problems with doing this so far for the type of policies we've been thinking about in this class? So far we've been thinking about mostly policies that are all deterministic, which means that they're mapping from states to actions, and we've been thinking about cases where this is a deterministic mapping. So we always pick a particular action for a particular state. Yeah, in the back. And name first, please. Oh, what's your name?
We'll never actually explore anything.
Okay, yes, but what's the problem? We're never exploring, which is correct, but what's the problem with not exploring?
We only sample one path over and over again, and we never actually learn anything about the rest of the world that we don't see. So we don't know whether there's a better policy somewhere else.
So what Brian's saying is saying that maybe we're going to only sample one path. I think what he means more than that is, so you can still sample different paths because your state space can be stochastic, but you're only going to ever try one action from one state. So you're never going to learn about what it would be like if you took A2 instead of A1 in that state, which means that when you're doing this, for any particular state, you'll only see one corresponding action. So the time, whenever you see state S1, the only action you'll see will be A1 or whatever your policy says to do there, which means that you're not going to have any information about doing anything else there, which means your policy improvement is going to be pretty boring because you're not going to get any other information about things you should be doing instead. So we're going to have to do some form of exploration. Essentially now we're going to have to start to have some sort of stochasticity in our policy, or it needs to be changing over time so that we can actually try different things even from the same state and learn what to do. Yes, name first.
Do we know the whole action space beforehand?
Great question. First question is, do we know the whole action space beforehand? Yeah, we're going to assume that we do for at least all of this lecture and in general. Yeah.
Okay, so then couldn't you make the actions initially have high values, so then after it's computed when it's probably computed something low, so the next time you see it, you would try the other action?
You just made a very nice suggestion. So that relates to how we're initializing the queues. So one thing you can do, which is what Christopher just suggested, is you can initialize your queue function really high everywhere. You can basically do what's known as optimistic initialization, and that actually can be a really useful strategy for exploration. And if you initialize it in a particular way, then you can have provable guarantees on how much data you're going to need in order to converge to the optimal policy. So optimistic initialization is often a really good thing to do. You have to be a little bit careful of how you initialize things, like what those values should be, but generally, empirically, it's really good, and formally, it can be very good too. We're not going to talk about optimistic initialization today, but we will later in the class, or talk about optimization.
So this method doesn't rely on the Markov assumption to be able to estimate Q, right?
Yes.
But my question is, whenever we're defining the policy, we only define it in terms of the state. And if the reward that you get from a state depends on the history you have, then that breaks the Markov assumption. And like, even though the reward is not Markov, then your policy is we're defining the policy as if it were.
Yeah, so what Carlo is asking about right now is an important point. So your real world may or may not be Markov. All the policies we're talking about right now is assuming the world is Markov. The policies are only mappings from current state to action. They are not a function of the history. So those may or may not work well because your real world may or may not be an MDP. And if it's not, then you're considering essentially a restricted policy class. You're considering only mappings from the immediate state to the action. And if what you should do really depends on the whole history, then you might not make good decisions. Great point. Okay, so this is sort of how the basic way you would extend Monte Carlo to be able to start to estimate Qs. And once you have them, you could do policy improvement. But now it's clear that we need to do something in terms of how we should gather experience so we can actually improve when we try to do this policy improvement. Because now we don't know how the real dynamics of the world work. So we need to do some sort of interleaving of policy evaluation and improvement. And we also need to think about how we're doing this exploration aspect. So in general, it might seem a little bit subtle. So we've already heard one nice suggestion from like maybe you could initialize everything optimistically and maybe that would help you explore. It does. But in general, it might seem like it's a little bit hard of how are we going to get this good estimate of Q pi? Because what Q pi does is it says, if you wanted a really good estimate of Q pi of SA for all S and all A, it would say you kind of need to get to every different state, take every possible action, and then follow pi from then onwards. And so how do I make sure that I visit all of those things? And what we're going to talk about today is sort of a very simple strategy to make sure that you visit things, which works generally under some mild conditions about the underlying process. Okay. So the really simple idea is to balance exploration and exploitation by being random some of the time. So let's imagine that there's a finite number of actions. We're going to call that cardinality A here. Then an E-greedy policy with respect to a state action value is as follows. With probability 1 minus epsilon, you're going to take the best action according to your current state action value function. And else, then you're going to take an action A with probability epsilon divided by A. So with probability 1 minus epsilon, you take what you currently think is best according to your estimate of the Q function. And with probability epsilon, you select one of the other actions. So it's a pretty simple strategy. And the nice thing is that it's still sufficient. But before we do that, why don't we just do a brief example to make sure that we're all on the same page? So let's think about how we would do Monte Carlo for on-policy Q evaluation for our little Mars rover. So now our Mars rover is going to have two things it can do instead of, and we're going to be reasoning more about that. So I've written down the reward function here of saying that if you take action A1, you get the same rewards we've been talking about before, which is 1, 0, 0, 0, 0, 0, plus 10. And now I'm changing it. I'm saying, well, your rewards do depend on your state and the action you take. And so the action for A2 is now going to be you get 0 everywhere, and then you get a plus 5 at the end, and gamma is 1. Now let's assume that our current greedy policy is you take action A1 everywhere, and that we're using an epsilon of 0.5, and we sample a trajectory from an E-greedy policy. And again, what an E-greedy policy means here is I've set epsilon equal to 0.5, which means that half the time we're going to take our current greedy policy of action A1, and the other half the time we're going to either take A1 or A2. So what that would yield, as an example, would be a trajectory such as state 3, action A1, 0, state 2, and now this is a case where we're sampling randomly. So we flipped a coin, we said, oh, this time I'm going to be random, then I have to flip a coin again to see whether I'm taking action A1 or A2, and I took A2 there. I got a reward of 0, and then the rest of trajectory as follows. And my question to you, and feel free to talk to a neighbor, of course, is what is now the Q estimate for all states for both action A1 and action A2 at the end of this trajectory using Monte Carlo estimates? So we're just doing first visit in this case. Yeah.
Quick question about the actions we choose in the epsilon case.
Yeah.
Is it important to include the action on policy when we hit the phase of exploration, or should we exclude that action from our action space that we like increase the chance of exploring and not sticking with policy?
The question is whether or not when you hit a now do something random, whether you should exclude the action that you would be taking normally if you're being greedy. You could, in some ways, that's like just picking a different epsilon. Yeah. I hear less talking than normal, so does anybody have any clarification questions about this? Or other questions? Cody?
We had an idea, but
Okay, yeah, so if everybody's ready to answer, so what did you guys think?
we're thinking, so you will have, in this case, S3, well, you initialize everything as 0 to begin with, right?
Yep.
So everything that you did not, every state action pair that you did not see will remain 0.
Yep.
And then in particular, Q of S3A1 will be 0 because you saw that once, and when you saw it, it was 0. Q of S2A2 will also be 0. Q of S3A1 will be 0. And then the only one that will be non-zero would be Q of S1A1, which in this case will be 1 because you saw it once, and the reward you got when you saw it was 1.
That is one answer. Does anybody have a different answer?
For these So should we count until the end? So all of the state action pairs that we've seen will be 1, and all other state action pairs will be 0.
That is another answer. So then we have a third answer. So what you were saying would be right for the TD case. What you were saying would have been right for last week, or yesterday, or on Monday, I guess. It may have a third answer.
Could you repeat what the second choice was?
So the first choice is that we only update S1, A1. The second choice is that everything that we saw will now be 1. And maybe I misunderstood what there is. So we're going to have two different, we have two vectors now. So we have Q of A1 and we have Q of A2. And they're not going to look identical. So sometimes we take action A1 and sometimes we take action A2. And we can only update what we saw, the returns for the action we took. So what actions did we take for S3? Just A1, right? So that means for those ones, for S3, it's going to be 1 under for Q of S3, A1. So I'll fill in all the ones that are 0. 1, 2, 3, 4. Did we ever take A2 in S3? No, so that also has to be 0 because we didn't ever start there, take action A2 and get a return. What about for, what action do we take from S2? Right, so for that one, we get a 1. So we basically, you're distributing your experience. So now if you were going to take a max over those, then you would get the same thing that we saw last time for Monte Carlo, which would be 1, 1, 1, 0, 0, 0, 0, 0 to the end. But here we're subdividing our samples. So you only get to get an experience for the action that you actually took in the state. And because we're in the Monte Carlo case, we'll see the TD case, or Q-learning we'll call it later, then we get to add up all the rewards to the end of the episode. So G here is going to be the sum over all of those steps. And I didn't specify, oh, I did, good. And we're keeping gamma equal to 1 here just to make all the math. Just adding. Yeah.
Would it just be 1/2 for the QS1A1 and QS3A1? Would that be the only difference because you visited both of those states twice?
The question was about whether or not if we did every visit, if anything would change here. Excuse me, it would not change in this case because both times when you visited S3, the sum of rewards to the end of the episode was 1. So you'd have 2 counts of 1 and then you divide by 2. It can actually be different, but it's mostly different if you got like a different sum of rewards from then to the end of the episode. Yes?
So isn't that answer
Remind me your name, please.
Isn't that answer exactly what Washington said before?
Maybe I misunderstood. So I thought you were specifying that everything was, and I missed it. Did you say that that was different for the 2 actions?
I said it was 1 for every state action pair that we have seen in the trajectory, and 0 elsewhere.
I missed, yes. Sorry about that. Yes. Great. Okay. Okay, so now we're going to show formally that this does the right thing. So we're going to show provably that, like what we did before when we were doing policy improvement, we were showing that if you picked a policy, pi I, that was generated by being greedy with respect to your Q function, then that was guaranteed to yield monotonic improvement. And the same thing is going to be true here too when you do E-greedy. So if you use sort of an E-greedy policy, then you can gather data such that the new value you get, if you're optimistic with respect to that, or sorry, if you're greedy with respect to that, then you're going to get a new better policy. Okay, so let's say that we have an E-greedy policy, pi I, and then we're going to call an E-greedy policy with respect to Q pi I, which is going to be pi I plus 1. So we had a E-greedy policy pi I that was doing some amount of exploration and some amount of greediness in the past. We used that to gather data. We then evaluated that policy and we got this Q pi I. And now we're going to extract a new policy. We're going to do policy improvement. And we're going to show that that's a monotonic improvement. Okay. So do we have any questions about what we're showing? Okay, so what does this mean? So right now what we're going to be trying to show is that this Q function of pi I of S pi I plus 1, so is going to be better than our previous value, at least as good or better than our previous value of our old policy, pi I. So the way we define this is now the Q function here is going to be a sum over, our policy is stochastic, so it's pi I plus 1 of the probability we take an action in a certain state times q pi I of SA. And then we're going to expand that out, and we're going to redefine it in terms of what it means to be an E-greedy policy. So remember in an E-greedy policy, we either take something randomly, and that's with probability epsilon, and we split our probability mass across all the actions. So that's how we get this equation. So this says, this is the random part. So with probability epsilon, we take one action, one of the actions, and then we would follow that from then onwards. So that's just q pi I of SA. And then with probability 1 minus epsilon, we're greedy. And we follow the best action according to our current q pi I. So now what we're going to do is we're going to rewrite that. The first term isn't going to change, and I'm going to expand the second. And I haven't done anything here. I just multiplied the last term by 1. But I expressed the 1 as 1 over epsilon divided by 1 over epsilon. And now I'm going to re-express that part. So I'm not going to rewrite the first term plus 1 minus epsilon max over A. And what I'm going to rewrite this as is going to use the fact that whenever we define our E-greedy policy, if you sum over all actions in a certain state, those are all probabilities of us taking those actions in that state, so it has to sum to 1. So I just multiply by 1, expressing it as 1 minus epsilon divided by 1 minus epsilon. Then I re-express the 1, because this has to equal to 1, because we have to take some action in a particular state. Our policy always has to, the probability of us taking any action in a state has to be equal to 1. And then I'm going to do that expression, because here is where we would take the best action. So by definition, the best action has to be at least as good as taking any of the other actions. So we're going to do the following. We're going to push that q inside. So that has to be smaller than what we saw before, because basically we just push the q inside and we're no longer taking a max. And the q values, all of the q values at best have to be equal to the max. In other cases, they'll generally be worse. Okay, but then once we have that, we can cancel that 1 over epsilon minus 1 over epsilon. And what do we have? We have two different terms here that look very similar. We have, oops, I made one mistake here. Let's see, I made one mistake in that part. I'll keep this. Yeah. There was an epsilon over A right there. Okay. So now I'm going to pull that out. Okay. So I split those terms up. The first term and the third term are identical, and one is subtracted and one is added. Make sure that's clear. And so this just ends up becoming the middle term. And that was just the previous value. Yeah, Scotty.
changed it to, instead of the sum over all A of pi I, A given S minus epsilon to minus epsilon over the cardinality of A in this case.
Yes.
Is that still 1 minus epsilon? Or that looks, oh,
That's all inside of this.
I see. Got it.
Does that answer the question?
I think so.
Yeah. So what we did from the 1 minus epsilon to the next line. So we had a 1 minus epsilon divided by 1 minus epsilon, and I re-expressed that as the sum over A, pi I of A given S, minus epsilon divided by sum over A. And then if you sum over A, that second term just is epsilon, and the first term is 1. Yes? Can you remind me your name?
Sorry?
Name?
Oh, Ben. Pi I instead of pi, like you wrote v pi I plus 1 greater than v pi. Let pi I.
Pi I plus 1. Which line are you thinking about? Which?
I mean, on the slide. The second line. Just go through.
Yep.
You wrote v pi I plus 1 greater than v pi. Instead of pi I instead of v pi.
I'm sorry, I'm still not understanding your question. So you're on the second line, is that right? Or
Second line on the slide, not what you wrote.
In the first sentence.
in the first sentence? Okay, pi I plus 1 is. Sorry, what is the question?
Well, on the slide you have v pi I plus 1 and v pi. I think it's v pi I instead of v pi.
Yes. Main typo?
Yeah.
Thanks. Thanks for catching it. Yeah, Camilla.
Can you explain how you went from equals to the greater than or equal to?
Yeah, so good question. The greater than or equals happened because we pushed that q pi. We had a max over A, q pi I of SA. And we pushed it inside of the sum. And so that sum now no longer includes a max. And so now the max is always greater than or equal to any of the other elements. So that's where you got the greater than or equal to. Yeah. Javen?
So I just wonder if you can explain, like, intuitively why that's the case. Because I think I understand the formulas, but I don't understand why you take some random suboptimal actions and then you end up with monotonic improvement.
Yeah, Javen had a question. So can we give some intuition? This is sort of the algebraic derivation. I think intuitively the idea is that by doing some E-greedy exploration, you're going to get evidence about some other state action pairs. And then you can use those to estimate your Q function. And that when you do that, then that's also going to give you, then that can improve your policy because then you can have evidence that there's something better you could do than the current thing you're doing. So if you don't do any exploration, your Q function wouldn't change from before. But now because you're doing exploration, then you can learn about other stuff. And then if it's better, you'll see that in your Q function.
So if it doesn't improve, you take the. So when you do the Q-val function, if like your exploration is not as good, then you just take the old ones, like the old values.
Yeah. Yes. So this is now, this is saying that you'll get this monotonic improvement if you're computing this exactly. So that's an important part. So what this shows here is that if you get a Q function and it looks like there's some improvement from some other actions that you're not taking right now, you're going to shift your policy over towards focusing on those actions. This is assuming right now in terms of the monotonic improvement that the Q pi i's have been computed exactly. So that's what we saw when we were doing planning, where we knew what the dynamics model was and the reward model, and we were using that to compute a value function. So if we were doing in that case, we had the guaranteed monotonic improvement because we had the exact value of pi. And similarly here, if we have the exact value of q pi I, then when you do this improvement, then you're guaranteed to be monotonically improving. If you didn't, like if you have just an approximation of q pi I, then it may not be monotonic. Like let's say you tried another action once in that state, you may have a bad estimate of how good things are from that point. So this is an important aspect. And this is going to be really important when we start to think about function approximation because we almost never will have computed q pi I exactly. But if you do, like let's say you can just iterate through this a ton of times, like you're learning that it's still a tabular environment, you've converged, you know your q pi I is perfect, then when you then do policy improvement, you can get a benefit. You can improve. And so there's going to be this interesting question of how often do you improve your policy versus how much time do you spend evaluating your current policy? Yeah.
Yes.
Yeah.
So does this mean that that definitely converges to like an optimal Q function.
In terms of what is the overall performance, yeah, we'll talk about that. The question is great. So this is just saying like one step monotonic improvement. What's going to happen in terms of total convergence? We'll talk about that in just a second. Yes. Remind me name, please.
It's probably a very easy question to answer. I just can't remember it right now. But when I think of pi, I think of it being a function of a state, and here we're using it as a function of an action given a state.
This question is just to sort of refresh all of our mind of like what is a pi and how we define the function. Now we're thinking of it as a mapping from states to actions, but it can be a stochastic function. So it can be a probability distribution over actions. So I can select action A1 with 50% probability or action A2 with 50% probability, for example, from the same state. No, taking a state.
Okay.
I mean, it depends how you want to implement it. Like that can start to be in it, but essentially I think of it as you're in a state, and then you have some probability distribution over actions, and you have to sample from that to decide what action you take.
And so here we're inputting a state.
The policy, so what we're doing here when we expanded this is we said, what is the policy for an action given a state? We said with 1 minus epsilon probability, we would be taking this max action, so that one. And with epsilon probability, we would be taking one of the actions. And so then we summed over each of the actions we could take. So what we did there is we split this sum up into the probability of taking one action and what would be the Q function of that action, and the probability of taking each of the other actions and what would be the value of those. So it's like our expected value. Yeah, in the back. Is it?
It's like when we talked about the Bellman operator, we said if you got to the same value function you had before, you know you can stop iterating. Here, like would you have to have tried every action to know that you're done?
That's a great question, which is before in policy improvement, if you got to the same policy, you knew you were done. You didn't have to do any more improvement. The question is, in this case, is it true or there's some other additional conditions? This is very related to question 2. So why don't we go on to the next part of saying, under what conditions are these going to converge and converge to optimal? Do you have a question before?
Yeah, just quickly. Does this also say that the only time we get strict equality is when epsilon is 1, so we just act purely randomly?
The next question is whether or not there's, so if the policy is random, would you get strict equality here? Yeah, you should get, you can get strict equality whenever you've converged too. Like if your Q function is converged and your policy is optimal.
Then you guarantee strict equality, I guess, when you're just acting totally randomly.
No, I don't think so, because if you're acting totally randomly, in fact, that's normally often how you start off and then you want to improve from there. Because if your reward isn't uniform, some things are going to look better than others. So even if you're acting randomly, some actions are going to have higher rewards than others, and that's going to be reflected in your Q function. Okay, any other questions before we get on to convergence? In the back.
Just a quick question. Where do you get the second inequality from?
What's your name? I think there's only one. Oh, sorry. This should, yeah.
Do you exclude the argmax when you explore?
Do we what?
Do you exclude the argmax action? Like you have like exploration part and the greedy part.
What's your name? Amadid? No, you don't exclude. You don't exclude the argmax action when you explore. You pick all of them. If you wanted to, that would be equivalent to sort of defining it. You could do that, but in the simplest version, including in this proof here, we assume that when you're acting randomly, you just sample from any of the states. It's often easier for implementation too. Okay, great questions. Let's, I wrote that up here as well. Okay, so this other really great question that's coming up from several people here okay, well, what does this mean over time? All right, we've got this monotonic improvement, and what guarantees do we have? So the guarantees that we have is if you sample all state action pairs an infinite number of times, and your behavior policy converges to the greedy policy. So what do I mean by that? So the behavior policy here is sort of what policy you're using versus what policy is greedy with respect to your current Q. Okay, so if you have the case that as the limit as I goes to infinity of pi a given s goes to argmax Q exponent A with probability 1, which means that in the limit, you converge to always taking the greedy action with respect to your Q function. Then you're greedy in the limit of infinite exploration. That's called glee often. So that means that you visit all your state action pairs an infinite number of times, but you are also converging, excuse me, in the limit to being greedy with respect to your Q function. And there's different ways to do this. A simple way to do it is to sort of decay your epsilon or your E greedy policy over time. So you can reduce your epsilon towards 0 with a rate of like 1 over I, for example. That's sufficient. It's not necessarily, this is separate than what you want to do empirically. This is just to sort of show under these conditions, then we're generally going to be able to show that we're going to converge to the optimal policy and optimal value for Monte Carlo and TD methods. So generally we'll talk about this again as we talk about some of the other algorithms. Generally when you're glee and you have some conditions over how you're learning the Q functions, then you will be guaranteed to converge to the optimal policy. Yes?
Is this the only way to guarantee that? Like by decreasing epsilon? And yeah, I guess that's my question.
Yeah, so the question is this the only way to guarantee it? There's sort of interesting different things that are happening here. You could be guaranteed that you're converging to the optimal Q function without converging to the optimal policy. So you could keep epsilon really high, and you could get a lot of information. You'd be learning about what the optimal Q function is, but you might not be following that policy. And we'll talk more about that in a minute. All right, so let's talk a little bit more about Monte Carlo control in the sort of given this precursor. So if we wanted to do Monte Carlo online control instead of just this evaluation we talked about before, we can kind of combine these ideas of learning the Q function and doing this improvement at the same time. So we can initialize our Q functions and our counts in the same way we were talking about before. And then what we can do is we can construct an E greedy policy. So our E greedy policy in this case is always going to be that with probability 1 minus epsilon, we pick the argmax with respect to Q, and with probability epsilon, we select an action. Let me rewrite it this way. Probability epsilon over A, we select action A. So we're always just mixing up between this random or being greedy. Yeah.
So actually, like the optimal action in this case, you're selecting with probability 1 minus epsilon plus epsilon over the cardinality A, right?
Exactly.
Okay.
Yeah. This is several people have asked about this. So essentially, you're being greedy with probability 1 minus epsilon plus epsilon over A. And then the remaining part of your probability is going to random exploration. Because when you're being random, you could also select what's currently the best action. So this looks pretty similar to what we saw before. We're going to sample an episode. After we finish the episode, then in this case, I'm defining it as first visit. Note, you could make this every visit. Could do every visit. The same benefits and restrictions apply here to what we had before in the sense that you could either be getting a slightly more biased estimator if you're doing every visit, but generally you're going to be able to use more data, so it's going to be sort of less noisy. So in this case, what we're doing is we're just maintaining counts over state action pairs and we're updating our Q function. And then after we finish that episode, then we can update our K and our epsilon. In this case, we're just using epsilon equal to 1 over K. And then we redefine our new E greedy policy with respect to Q, and then we get another episode. So that's just sort of Monte Carlo online control. So why don't we go back to that Mars rover example. So in the Mars rover example, what we had is this is what our two Q functions look like. So at this point, what would be, let's just spend a minute and say, what would be our new policy? If we're at the end of this episode, and it's fine just to write down tie. If there are two Q functions that have exactly the same value for the same state for two different actions, and there's just a tie, and you can choose how to break the tie, and then also write down what the new E greedy policy is. I'll just take a minute to do that. Okay, what's our greedy policy? What's our greedy policy for S1? A1? What's our greedy policy for S2? And then what's our greedy policy for S3? And then what's it for everything else? Tie, okay? And depending on your implementation, you could either sort of define your greedy policy, or you would just like break ties randomly and keep track of that. You could constantly be breaking ties randomly. That would probably be better empirically. Like instead of predefining one greedy policy, you can probably just always be querying what argmax is of Q. And if you're getting ties, just break them randomly to get more exploration in. So then if we then define an E-greedy policy where K is 3 and our epsilon is 1 over K, with what probability do we follow random? So K is 3, epsilon is equal to 1 over 3. So that would mean that with 1/3 probability, we select something random, and with 2/3 probability, we select the pi greedy policy. Okay. And then that would be the update for that particular episode. So if you do this, if you have greedy in the limit of infinite exploration Monte Carlo, then you're going to converge to the optimal state action value. So now we're going to start to talk about TD methods. So similar to what we were seeing for Monte Carlo, there's going to be sort of a simple analogy that moves us over to TD. So remember, for TD, what we had before is we'd have our V pi of S. It was equal to our previous V pi of S plus 1 minus alpha times, oops, let me rewrite that, plus alpha times R plus gamma V pi of S prime minus V pi of S. And this was where we were sampling an expectation because we were only getting one sample of S prime, and we were bootstrapping because we were using our previous estimate of V pi. So that was kind of the two key aspects of TD learning, is that we were both bootstrapping and sampling. In Monte Carlo, we were sampling but not bootstrapping. And one of the nice aspects of TD learning is that then we could update it after every tuple instead of waiting until the end of the episode. So just as like what we were doing with Monte Carlo, we were kind of replacing all of our V's with Q's, we're going to do exactly the same thing here. So now we're going to think about this sort of what's often known as temporal difference methods for control. So what we're going to do now is we can estimate the Q pi function using temporal difference updating with like an E-greedy policy. And then we can do Monte Carlo improvement by setting pi to an E-greedy version of Q pi. So that would be one thing we can do. There's an algorithm called SARSA, which stands for state, action, reward, next state, next action. So SARSA. How does SARSA work? So what we do is we initialize our E-greedy policy randomly. for example. We take an action, we observe a reward in next state, and then we take another action and we observe another reward in next state, and then we update our Q as follows. We say our our value of Q for STAT is going to be whatever our previous value was. Actually, I'm going to be careful with this. We're not going to index them with pi anymore, because we sort of have this running estimate, and our policy is going to be changing too. So the Q function that we get here is now not just for one policy, but we're going to be averaging over different samples, and we can be changing how we're acting over time. So it's STAT. It's going to be equal to Q of STAT plus 1 minus alpha RT plus gamma Q of ST plus 1 AT plus 1 minus Q of ST AT. Okay. The important thing about this equation is that I am plugging in the actual action that was taken next. So you see, you're in a state, you do an action, you get a reward, you go to a next state, and then you do another action. And so once you know what the next action is that you've done, then you can do this update in SARSA. Okay, so you're actually plugging in the action that was taken. And then once you have that, you can do policy improvement in the normal way. So you can have ST is equal to arg max Q. Or so like the E-greedy wrapper for that. Now, so this is a little bit different than Monte Carlo for two reasons. It's sort of, we're doing these tuple updates. We see the state, action, reward, next state, next action tuples. And then once we do those, we can update our Q function. But we can do those along the way. We don't have to wait till the end of the episode. And similarly, we don't have to wait till the end of the episode to change how we're acting in the world. So like in the trajectory that we saw before, we saw some states multiple times. In this case, we could actually be changing our policy for how we act in those states during the same episode. So if your episodes are really long, this can be really helpful. So in general, I think it's often extremely helpful to update the policy a lot. Yeah?
Is there a reason that there's like an alpha here, 1 minus alpha in the previous slide?
Sorry, what?
Oh, sorry, like up here it's alpha, but here it's 1 minus alpha. Is there like a standard?
Oh, yeah, so they're both the same. It's just either you can write it where you put the V in the next part or not. So you can either have it as 1 minus alpha times your old value plus reward plus gamma of your next thing, or you can have it as V plus alpha times, so that should be still an alpha here, plus reward plus minus V. So that's either 1 minus alpha. They're the same. If you notice I've made a typo, just let me know. Yeah?
And is there a reason you use like the next state action pair that you choose, like
Plus 1 rather than the max state action?
The question is about why do we use the next state action pair you choose instead of the max. Q-learning is going to be the max. We'll see that in about a slide. SARSA is basically updating on policy. That can have, generally you want to do Q-learning, which is going to be doing the max. Sometimes there are some benefits, particularly in cases where you could have a lot of negative outcomes, that the optimism of being max can end up sort of causing your agent to make a lot of bad decisions early on because it's really optimistic about what it's could do instead of what it's actually doing. There's a nice cliff walk example inside of Sutton and Bartow where they show that SARSA actually is doing better in sort of early stages, early samples compared to Q-learning because SARSA is realistic about what happens if you take certain actions next as opposed to optimistic. And if you're doing a lot of randomness, that means that SARSA can be more realistic in the early stages. But empirically, generally, you want to do Q-learning, and both will converge to the same thing. Yeah.
So in line 7, should the Q ST1 T plus 1 be ST plus 1 instead?
Yes, thank you. It should be ST plus 1. Thanks for the catch. Yes.
This might be a nomenclature question, but you're talking about how it's getting the information from the future action, but you have to have already done that action. So why is it called state action reward next state action when it's really the past one that you're updating, from what I'm understanding? Because you're doing this one, then you're using the information you learned to update the one in the back. So why are we talking about it like it's a future action? What's the purpose of that?
I don't think the question is about the particular terms used to define star set. I don't think I mean, I guess it's really just that you have to wait till you get that last A is important. So that instead of saying that, but before what we saw with TD learning is you were in a state, action, reward, next state, and then you could update your queue function. Now we're just saying you have to wait till you've actually decided what to do in that next state. Because that's how you're choosing how to update your queue function here. Because that's what you're plugging in for your target. So in terms of the convergent properties, it requires a couple different things. So if we are, we need sort of two things. We're going to need the fact that we're updating our queue function, and it's going to be updating incrementally. And so like what we talked about before, we're going to need some conditions over the alphas. If alpha is equal to 1, generally your queue function is not going to converge because it means you're not remembering anything about the past. If alpha is 0, then you're not updating anymore. So generally you need something in terms of the step sizes, which allows you to sort of slowly be incrementing but still be converging. So these are one sufficient set of conditions. So if you have stuff like alpha t is equal to 1 over t. Now empirically, often you're going to want to pick very different forms of learning rates. So alpha t is often referred to as like the learning rate parameter. And empirically, you're often not going to want to use this. Generally not going to want to use this. This is going to, you're often going to want to use different things empirically. You can end up using sometimes small constants or slowly decaying constants. It's often going to depend on the domain, but this is, from a theoretical side, what is sufficient to ensure convergence. And then the other aspect is that the way that your policy itself has to satisfy the condition of glee, which means that you are sort of slowly getting more greedy over the time, but you're doing so in a way that you're still sampling all state action pairs an infinite number of times. Now I'll just note for a second that that's not always possible. Like, so if you have a domain where things are not reachable after a point, it's not ergodic, you can't get back to certain states after you get there. Let's say you're flying a helicopter and you break the helicopter, so you can't get back up there. Then you're not going to be able to satisfy glee because at some point you broke your helicopter and then like you have no idea what it would have been like if you continued to fly your helicopter in the air. So there can be some domains for which it is very hard to satisfy glee, but we generally are going to ignore those, even though there's some really interesting work on sort of how do we deal with those cases as well. In those cases, something you might assume is that it's more of an episodic problem. So maybe you have like 100 helicopters, and so when you crash one, that's considered a termination condition, and then you get out your next one. So you may or may not be able to be greedy in the limit of information, in the limit of infinite exploration there, but you can sort of have a bounded amount of exploration. And we're going to talk a lot more later about sort of how to do this exploration in a much more smart manner and in a way that can give us finite sample guarantees on how much data we need to learn a good policy. So this just says what I said there before, which is, we generally are not going to use the step size.
With the alpha t here, this is assuming a particular form of our update, right, which is where you have q of STAT plus alpha as opposed to 1 minus alpha times the update. Is that correct?
Yes.
Okay.
Yeah, so this is for SARSA. So this is the conditions for SARSA, assuming that that particular update of how we're updating our queue functions. Okay, so yeah.
My name's so in the Monte Carlo case, we had the sufficient condition on like the pi t satisfying glee, like the epsilon's going down as 1 over k. Do we have anything similar in general?
Great question. The question is about for the Monte Carlo, do we have a similar condition? If you were just, if you're doing first visit, that alone is sufficient because you're getting an unbiased estimator that's converging for all of your returns. So as long as you visit all state action pairs an infinite number of times. If you're doing it in this incremental fashion, then if you're if you're playing around with how that alpha is, then you need to have similar conditions to make sure it guarantees.
What I mean is, how do you know that condition 1 holds?
How do you know that things are glee?
Yeah, like in Monte Carlo, we did have a condition, right? Which was that epsilon's decay is 1/k.
Oh, so great question. So Ben is like, how do you make sure something's glee? One sufficient condition is that epsilon is 1/t or 1/I.
And do you know like characterization of the sequences of epsilons that work? Like, yeah.
Oh, you mean like in terms of sufficient conditions like this?
Yeah, or like it'll be glee if and only if the epsilons go to 0, but there's some diverges or something like that.
Yeah, I think it's probably similar to the same Robbins-Monroe sequence. Similar, like you're sort of essentially you're ensuring you're sort of doing infinite number of updates, infinite amount of like random exploration, but still it's going down fast enough that it's converging. I think it's probably exactly the same, but I can double check. Okay, so then when we get into Q-learning, which is related to the question we just asked of, hey, why are we picking that particular action next? Why don't we just pick the max? Yeah, we could just pick the max instead. So SARSA is picking this particular action next. Q-learning is picking the max action next. Yeah.
Can we mix them? Because you said like SARSA tends to do better early on because it's not so optimistic, and the Q-learning does better later.
So the other question is whether we could mix SARSA and Q-learning. You certainly could, but then that also made me realize maybe I wasn't being clear enough for the earlier part. So SARSA can do better in some domains early on, particularly if there's a lot of really negative rewards because it's being realistic. In other cases, Q-learning will be better even early on because you're being more optimistic. And as we talked about a little bit before, often optimism is really helpful for exploration. The cliff rock example in Sutton and Bartow is a case where some actions lead the agent to like fall off a cliff, and so some actions are really bad. And so there being optimistic early on means that you're going to take a lot of really bad decisions and suffer a lot of negative rewards for a while. Many other domains, they're not like that. So it depends a lot. But yes, you could certainly mix them. All right. So I guess in terms of Q-learning, one thing that's interesting here is so we can again sort of think about how we're improving this, and we're going to sort of be greedy with respect to the current estimate of the optimal Q. And really this is quite similar to what we were doing in SARSA, except for now when we update this Q, we're really just going to be doing this max. So Q of ST AT is going to be equal to the previous value plus alpha reward plus max over A. And so now also note that you can update this a little bit earlier because you don't have to wait until the next action is taken. So you only need to observe this part. You don't need to actually see the next action that's taken. And then you can perform policy improvement. And in general, in this case, you only need to update the policy for the state that you were just in. So you can update pi b for ST for the action you just took. You don't need to, particularly in large state spaces, that can be helpful. So we actually ended up talking about this a little bit already, about whether or not how you initialize Q matters. It doesn't asymptotically. I mean, if you have a case where your Q function is going to converge to the right thing, it'll still converge to the right thing no matter how you initialized it. So if it satisfies these other conditions. But it certainly matters a lot empirically. And so even though often we think of just initializing it randomly or initializing it with 0, initializing it optimistically is often really helpful. So we'll talk more about that when we talk about exploration. Yeah.
On the previous slide, should line 6 be a max, not an hard max?
Yes. Thank you. So now if we do Q-learning, let's see. I think I'm going to leave this as just an exercise you can do later, but you could just do the exact same exercise for Q-learning and see how these updates propagate. So just like Monte Carlo versus TD for policy evaluation, there's some of the same issues with Q-learning. Q-learning is only going to update your Q function for the state you were just in. So even if it turns out later in the same episode, you get a really high reward, you're not going to back propagate that information at the end of the episode in the way that you would with Monte Carlo. So Q-learning updates can be much slower often than Monte Carlo. And so that has implications for how quickly you can learn to make better decisions. So the conditions that are sufficient to ensure that Q-learning with eGreedy converges is basically the same as Sarsa. We need to make sure that things are that are glee. And actually, I can slightly revise this. So if you just want to make sure that you converge, then you need to visit all SA infinitely often. And you need to have these conditions on the alpha. So if you look at the same conditions, in order for the Q functions to converge, you need to have these conditions on how you're updating your, like what your learning rates are, and that you visit all state action pairs infinitely often. But that just isn't, that's sufficient to allow you to converge to the optimal Q values. And then if you want to actually make sure that the policy you're following is really the optimal policy, then you need to be glee, because you also need the policy you chose to be more and more greedy. All right, let me get just briefly into the maximization bias before we finish. So maximization bias is an interesting question. So why are we going to talk about this? Well, okay, let's go back to this one. So in Q-learning, what are we doing? Q-learning, we're computing a Q function, and then we're being e-greedy with respect to it. And then we're getting some more data, and we're re-updating our Q function, and we're being greedy with respect to it. And so or e-greedy with respect to it. And so we're always sort of doing this dance between updating stuff, getting more evidence, and then trying to kind of exploit that knowledge up to some random exploration. And the maximization bias points out that maybe there can be some problems with this. Okay, so let's just consider a particular example. Imagine there's a single state MDP, which means there's only one state. But there are two actions, and both of them actually have 0 mean random rewards. So now you can think of these as being like Gaussians. Right now, we're mostly talking about it when the reward is actually deterministic, but it doesn't have to be. It could be a stochastic reward. But in this case, we're going to imagine that whether you take action A1 or action A2, your expected value is 0, but the value you get on any particular step might not be 0. It might be, 1 or -1 or things like that. The average is still 0, but on any particular step, you could have something different. Okay, but the expected value is 0. And so the Q value for both SA1 and the Q value for SA2 is 0, which is the same as the value. And these are all, the optimal Q and S values. So let's imagine that there's some prior samples. You've tried action A1 a bunch of times, you've tried action A2 a bunch of times, and you compute an empirical estimate of this. And here again, where there's just a single state, and we can just average over these. So let's imagine that it's super simple, that we have gamma is equal to 0, so we're really just estimating over the immediate reward. Okay, so there's no future rewards. We're just saying all the times that we've tried this action before, what were all the rewards we get, and we average. And now what we want to do is we want to take our empirical estimates of the Q function for A1 and A2, and we want to figure out what the greedy policy is. And the problem is that can be biased. Okay. So even though each of these unbiased estimators of Q are themselves, even though the two estimates of the actions are unbiased, when you take the max over it, it can be biased. So let's just write out what that is. So our V pi hat is equal to the expected value of max over Q A1, Q A2. Okay. So I'm going to take the expected value of our max of these two things, because that's how I define my policy. My policy says pick whichever of these two empirically looks best. But we know that from Jensen's, this is greater than or equal to if you switch the max and the expectation. And this is just equal to max of 0, 0. So the important part is this. So, and this is equal to the true V pi. So that means that whatever we compute can be a biased estimator of the true V pi. So why does this happen? Well, if you get if you only have a finite number of samples, if I have tried action A1 a finite number of times, it might be on that finite number of times, it happens to look slightly positive. Like it's like 0.01 instead of 0. And then when I take my policy, I'm going to maximize over those, so I'm going to immediately exploit whichever one happened to look better, even if it was statistical chance. So that's why you can get this maximization bias. And the same thing can happen in terms of MDPs. So this generally can happen. You can also look at some nice examples from this paper by John Zitzicklis and Shai Minor, where they show how this can also happen in Markov decision processes, where essentially if you're estimating through these Q functions, then you're going to be sort of biased to whatever has happened to look good in your data, and so you can have a maximization bias. So one thing that was proposed to try to deal with this case is called double Q learning. And so the idea is instead of having one Q function, we're going to have two different Q functions. And we're going to create two independent unbiased estimators of Q. And you're going to use one of them for your decision making and the other to try to estimate the value. And that's going to allow us to have an unbiased estimator. And the reason that you might want to do this is because then it can sort of help with this issue that you can end up being overly biased towards things that have happened to look good yet. Now you're sort of separating like between the samples that you're getting to estimate how good an action is versus the way you're trying to estimate your policy. So I'm just going to be a little brief with this because of time. Double Q learning basically means that we're going to have these two different Q functions. And then with 50% probability, we're going to update one, and 50% probability, we're going to update the other. So this would, and in this case, I'm going to skip, I'll add this in the final slides. I want to show you the difference. So the difference here can be significant sometimes. So in this case, this is sort of looking at the percent of the time that we're taking bad actions in this domain, where you can have, in this case, you have a scenario where it's actually the wrong thing to do, but it's stochastic. And so with a small amount of data, it can end up looking better compared to another option where the reward is deterministic and actually better, but has no stochasticity. And then Q learning can suffer quite a lot from this maximization bias. If you're using the same Q function to essentially immediately define your policy as you are for estimating the value of that policy, whereas double Q learning does a lot better in this case. So it's something to consider in terms of when you're implementing these things, and it's a pretty small overhead too, because you can just maintain two different Q functions. All right, I know that was a little bit fast. I'll make sure to put details in there when we upload the additional slides today. The main things that you should know from today is to be able to understand how you do this Monte Carlo on policy control, and same for SARSA and Q learning. It's useful to understand how quickly they update, both in terms of whether you have to wait to the end of the episode and then how quickly information propagates back, and then also to understand how to define the conditions on the algorithms converging to the optimal Q function. Thanks.